Hello friends, I welcome you to my lecture on conversion of integral equations into differential equations. What we will do is, first we will begin with a differential equation, initial value problem, and we shall convert it into a integral equation. As we have already seen in our previous lectures, that when we consider an initial value problem and convert it to an integral equation, we obtain a Volterra integral equation of the second kind. Now, what we are going to do is, now we shall be converting this Volterra integral equation into the initial value problem. So, the one method which we had discussed earlier, where we assumed the highest derivative occurring in the differential equation as the known function by phi x, if we cannot apply that method to recover back the initial value problem. So, there is another method which can be used to convert a given initial value problem into the Volterra integral equation of the second kind, and then recover back the initial value problem from the Volterra integral equation. So, this is what is the initial value problem here: by double dash x minus sin x by dash x, by double dash x minus sin x by dash x plus e to the power x into by x equal to x, and we are given the initial conditions: by 0 equal to 1, by dash 0 equal to minus 1. So, what we want to do is, we will first get the integral equation associated with this initial value problem, and then we shall recover this initial value problem from the integral equation, resulting integral equation. So, what we do is, let us write this differential equation as by double dash x equal to by dash x into sin x minus e to the power x by x plus x. Then we integrate this equation with respect to x. When we integrate it with respect to x from 0 to x, what do we get? 0 to x by double dash x into dx equal to integral 0 to x by dash x into sin x dx minus integral 0 to x e to the power x by x dx plus x square by 2, which is the integral of x and evaluated over the limits 0 and x. So, here when we integrate by double dash x, we get by dash x, the value of by dash x at x is by dash x minus by dash 0, and by dash 0 is given to be equal to minus 1. So, left hand side will be by dash x minus by dash 0 equal to by x 0 to x by dash x into sin x. We can integrate that by parts. The integral of by dash x is by x into sin x 0 to x, and then we are integrating by parts, so integral 0 to x, and we have by x here into the derivative of sin x. Derivative of sin x is cos x, and then we have minus integral 0 to x e to the power x by x dx. So, we will get integral 0 to x e to the power x by x dx, and then we have x square by 2, because its value at 0 is 0. So, x square by 2, and by dash 0 is equal to minus 1. So, we will have by dash x plus 1 here, and that can be taken to the other side. So, we have by dash x equal to, here by x into sin x. At x it is by x sin x, but at 0 sin x is 0. So, we shall have by x into sin x minus, we can combine these two integrals because their limits are of integration are same. So we shall write minus 0 to x e to the power x plus cos x into by x dx plus x square by 2 plus by dash 0. By dash 0 is minus 1. So we have by dash x equal to by x sin x minus 0 to x e to the power x plus cos x into by x dx plus x square by 2 minus 1. Now let us again integrate this equation. When we integrate it again, what we will have by x 0 to x and then integral of by x into sin x over the interval 0 to x 0 and then minus 0 to x. So here we shall have double integral. This is by x minus by 0 equal to integral 0 to x by x sin x minus double integral e to the power x plus cos x into by x dx and then plus integral of x square by 2 will become x cube by 6 and minus. So by 0 is equal to 1, we can put the value of by 0 as 1 here and what do we get here? By x equal to integral 0 to x by x sin x. This double integral can be converted into a single integral. So minus 0 to x minus t into e to the power t plus cos t into by t dt plus x cube by 6 minus x and by 0 is equal to 1, so we get plus 1 here. So we get x cube by 6 by x equal to x cube by 6 minus x plus 1 integral 0 to x. Then we have this minus sign can be taken inside the integral. So minus x minus t into e to the power t plus cos t plus sin t into by t dt. So I have missed out sin t here because we are combining this integral and this integral. So we have combined this two. So I can write it as x cube by 6 minus x plus 1. We can combine the two integrals and write it as 0 to x minus x minus t e to the power t plus cos t plus sin t into by t dt. So this is what we have, and it is a as we can see, it is a Volterra integral equation of the second kind, because the unknown function by t occurs inside the integral here where the limits of integration are 0 and x. So both the limits are not constant. So this is a Volterra integral equation of the second kind. Now let us recover the initial value problem from this integral equation. So we shall begin with the equation here, this one by x equal to x cube by 6 minus x plus 1 plus integral 0 to x minus x minus t into e to power t plus cos t plus sin t into by t dt. We shall begin with this integral equation, and we shall obtain the initial value problem with which we started and got this integral equation. So what we will do, let us differentiate it with respect to x. When you differentiate it with respect to x, what you get is by x becomes by dash x and x cube by 6, when you differentiate you get 3x square by 6, so you get x square by 2, and minus x becomes minus 1, the derivative of 1 is 0. Then then you have to differentiate this integral with respect to x. So let us see how we get this. So when you differentiate, what you are getting is by dash x equal to 3x square by 6, so x square by 2 minus 1, and then d over dx of this integral. So we are differentiating the integral where the limits of integration are not constants. One is 0, which is a constant, the other one is a variable x. So let us recall the formula for differentiation under the sign of integration, which is the Leibniz rule. And so let us apply the Leibniz rule, d over dx of integral gx to hx fxt dt. This is nothing but integral gx to hx, partial derivative of fxt with respect to x dt, and then plus the value of the integrand fxt at the upper limit, which is f x hx, then derivative of the upper limit with respect to x, so dh by dx, minus the value of the integrand at the lower limit, so f x gx, and then the differentiation derivative of lower limit at with respect to x, so dg by dx. So let us apply this formula to differentiate this. So this is x square by 2 minus 1 plus integral 0 to x delta over delta x minus x minus t e to the power t plus cos t plus sin t into yt dt plus instead of t we put here x, so we get minus x e to the power x plus cos x plus sin x into by x, and then d over dx of x minus we now put in the integrand t equal to 0. So we get minus x minus 0 e to the power 0 plus cos 0 plus sin 0 into y 0 into d over dx of 0. Okay, now what we get is so thus by dash x is equal to x square by 2 minus 1, and when we differentiate here with respect to x, what we get plus integral 0 to x, so this is minus x plus t, okay, into e to the power t plus cos t. When we differentiate with respect to x, what we will get is minus 1 here, so minus 1 into e to the power t plus cos t derivative of sin t with respect to x will be 0. So we have into by t dt. And here x minus x is 0, so we are multiplying this thing by 0, and then here we have sin x into by x, derivative of x with respect to x is 1, so we get plus by x into sin x. Here what we are doing, this expression is multiplied by 0 into d0 by dx, d0 by dx is 0, so this whole thing becomes 0. So we get the following. So you can see we get by dash x equal to x square by 2 minus 1, and then minus sign from the integral can be taken outside. So we have minus 0 to x e to the power t plus cos t into by t dt plus by x into sin x. Now let us at x equal to 0, let us see here, when you put x equal to 0 here, we get this is 0 minus 1, integral limits are 0 0, so the value of the integral is 0, so y dash 0 equal to minus 1. Now let us differentiate it again with respect to x. So let us differentiate this equation again with respect to x. So we get y double dash x equal to 2x by 2, which is x, derivative of minus 1 is 0, minus d over dx plus d over dx 0 to x minus with this minus I can write here outside. So minus 0 d over dx and take e to the power t plus cos t into by t dt plus derivative of by x into sin x with respect to x. So we can apply here the formula for the derivative of product of two functions. So we shall have by dash x into sin x plus by x into derivative of sin x is cos x. Now let us again apply the Leibniz rule here. So you can see here the integrand does not depend on x, therefore when we take the derivative of the integrand, that is we take this first term we evaluate, so partial derivative of this e to the power t plus cos t by t with respect to x will be 0, so this part will become 0, and therefore we shall have to write x minus we evaluate the value of the integrand at the upper limit. So we get e to the power x plus cos x into by x into d over dx of x, and then at the lower limit is 0, so minus we evaluate the integrand at the lower limit, so e to the power 0 plus cos 0 by 0, and then we differentiate 0 with respect to x. So that is all. So we have y dash x sin x plus by x into cos x. This is 0 because derivative of 0 is 0. So what we have is x minus by double dash x equal to x minus e to the power x plus cos x into by x, derivative of x with respect to x is 1. So we have the following. So we can write or by double dash x will be equal to x minus e to the power x plus cos x into by x plus by dash x into sin x plus by x cos x we can see that when we multiply by x here and simplify, so this is further equal to e to the power x cos x by x into cos x. This term will cancel and we shall have x minus e to the power x into by x plus by dash x into sin x, or we can write it at thus by double dash x minus by dash x into sin x plus e to the power x into by x equal to x. So, we have got the differential equation back. With there were two initial conditions. One initial condition was the value of by at 0, the value of by at 0 we needed. So, that value of by at 0 we can see from the Volterra integral equation which we started. Here you put x equal to 0, so this is 0, this term is also 0 and the integral will be 0 because the limits of integration will be both 0. So, by 0 equal to 1 we can see from the given Volterra integral equation of the second kind, and by dash 0 equal to 1 we got when we differentiated this Volterra integral equation of the second kind with respect to x. So, we have got the second order differential equation with the two initial conditions, and therefore, we have got back the initial value problem. So, this is how we recover the initial value problem from the integral equation. Now, let us so this is what we have. Now, let us go to the case of a boundary value problem. We shall see how we can get the boundary value problem back from the integral equation. Now, we have earlier seen in previous lecture that the boundary value problem can be converted into a integral equation, and the integral equation that we get is Fredholm integral equation of second kind. So, if you consider this boundary value problem by double dash plus x y equal to 1, where the two boundary conditions are given at x equal to 0 and x equal to 1, by 0 is given as 0, by 1 is equal to 0. Then in the previous lecture we have seen that this boundary value problem, when it is converted into an integral equation, the integral equation that we get is this Fredholm integral equation of second kind, by x equal to x into x plus 1 by 2 plus integral 0 to 1 kxt into by t dt, where we had obtained kxt equal to t square into 1 minus x 0 less than or equal to t less than x, and xt into 1 minus t when t lies between x and 1. So, x is less than or equal to t less than or equal to 1. Now, let us see how we can obtain the from this integral equation, from this Fredholm integral equation of second kind, the boundary value problem by double dash plus x y equal to 1, where y 0 and y 1 are both 0 at x equal to 0 and x equal to 1. So, let us see how we get this. Okay, so, we shall begin with the Fredholm integral equation by x equal to x into x plus 1 by 2 plus integral 0 to 1 kxt by t dt where kxt is t square into 1 minus x 0 less than or equal to t less than x, and x into 1 minus t xt into 1 minus t when x is less than or equal to t less than or equal to 1. Okay, so the integral equation can be written as, let us substitute the value of kxt, x into x plus 1 by 2 plus we break the interval 0 to 1 into two parts, 0 to x and x to 1. So, we get 0 to x over 0 to x interval, the value of kxt is t square into 1 minus x into by t dt, plus the integral, the value of the kxt is xt into 1 minus t over the interval x to 1. So, x to 1 xt into 1 minus t into by t dt. Okay, now we shall have to differentiate this in order to get the boundary value problem. So, let us differentiate it with respect to x. So, y dash x equal to, this is x square plus x, so 2x plus 1 by 2 when we differentiate. Now, here d over dx of integral 0 to x t square into 1 minus x into by t dt, plus here 0 d over dx of x to 1 x t into 1 minus t into by t dt. So, for the differentiation we have to apply the Leibniz rule of differentiation under the integral sign. So, this is 2x plus 1 by 2 plus, okay. So, this is your fxt, this is your fxt. When you when you differentiate this integral, so we have to take the partial derivative of this fxt. So, delta over delta x of t square into 1 minus x into by t dt into by t, and then we have dt. Then we put the t equal to x. So, we have x square into 1 minus x into by x into dx by x dx, minus we put t equal to 0 in this integrand and then differentiate 0 with respect to x. So, that term becomes 0. So, let us not write that. Then we have integral x to 1, we differentiate this with respect to x. So, xt into 1 minus t into by t plus, now we put x t equal to 1. When you put t equal to 1 in the integrand, that is the upper limit, and differentiate 1 with respect to x, derivative of 1 with respect to x is 0. So, that term will become 0, and then we put the lower limit in this integrand and differentiate with respect to x and put it negative sign. So, we write here minus sign. So, we put t equal to x here. So, x square into 1 minus x into by x into dx by dx. So, if you simplify this, what we get is this. So, this will give you y dash x equal to 2x plus 1 by 2, and then derivative here, let us write derivative with respect to x. Now, this is t square by t minus t square x by t. So, we will get minus t square by t here. This is x square times 1 minus x into by x. Derivative of x with respect to x is 1, and then x to 1. When we differentiate here with respect to x, we get t into 1 minus t into by t dt, and then we get minus x square into 1 minus x into by x. So, by dash x, let us see how much we are getting. 1 plus 2x by 2, 1 plus 2x by 2 minus 0 to x, okay, t square by t dt, and you can see here this term and this term cancel. So, we get plus integral x to 1 t into 1 minus t by t dt. So, this we have got the same value here. Now, let us go to second derivative. So, when you differentiate it once more, by double dash x becomes 2 by 2, that is 1 plus, now derivative with respect to x. We can put a negative sign here. We have this. Now, again we use the Leibniz formula. This is minus, then d over dx, the derivative, partial derivative of t square by t will be 0. So, first term will be 0. We put here t as x, so x square by x, then dx over dx. We put t as 0, then differentiate 0 with respect to x, so derivative is 0. So, we have this, and then here again when we take the partial derivative of this integrand with respect to x, it is dependent only on t, so its partial derivative will be 0, so this term will be 0. So, let us see, we can write it as x into 1 minus x by x dx over dx, and then this will be, when we put upper limit, we get 1 into 1 minus 1, because the upper limit is 1, by 1 into d1 over dx minus x into 1 minus x into by x into dx over dx. So, what we get is 1 minus x square by x, and this is 0. Okay, we have minus x into 1 minus x by x. We can open this, so we get 1 minus x square by x term will cancel, so minus x into by x. So, we get by double dash x plus x by x equal to 1. Now, from the integral equation with which we started, here we can see here, when you put x equal to 0, what do you notice? Okay, because we need to find by 0 at 0, by 0 is equal to 0, by 1 equal to 0. So, when you do see that, what we get? Let us see here, this is in the integral equation. When you put x equal to 0, this is 0, okay, and here this integral is also 0 because both the limits are 0, 0, and here when you put x equal to 0, the integrand becomes 0, so integral becomes 0. So, by 0 equal to 0 we get from this integral equation, and when you put x equal to 1, when we put x equal to 1, but what we get is this is 0 at x equal to 1, and at x equal to 1 this is also 0 because the integration limits are 1, 1. So, we get that, and at x equal to 1 this is by 1 equal to 1. So, by 1 equal to 1 we are getting. This is what I have to discuss in this lecture. I thank you very much for your attention.